Hey everyone, Mr. Cummings here, and in this video we're going to take a look at elastic collisions, inelastic collisions, and explosions. And these are all pretty common types of problems that we're going to analyze in our momentum unit. So the first type of collision we'll look at is an elastic collision. So we consider a collision to be elastic if the objects bounce off of each other, if the total kinetic energy of the system is conserved, and the total momentum of the system is conserved. And so all of these conditions have to be met for the collision to be elastic. So in our example here, we have two carts that are colliding, and it's hard to tell, but I've actually placed opposing magnets in each cart so that when they collide, the collision is a better approximation of an elastic collision. The magnets are going to repel each other without or with minimal loss of energy to heat, thermal, and things like that. Which brings us to a pretty good point here, and that is that true elastic collisions, especially mechanical collisions, are pretty rare in the real world, as some small fraction of energy is always going to be dissipated into heat energy or thermal energy, sound energy, maybe even deformation of the material. So if you have a car bumper that gets bent, that takes energy to bend it and to deform it. So while true elastic collisions are pretty rare in the real world, there are a lot of good approximations of elastic collisions, and considering a collision to be elastic is a good first approach to solving a lot of problems. So the next type of collision that we have is an inelastic collision. And so just a note here about the name, I will sometimes refer to this as non-elastic because it can be a little bit confusing when you use in a sentence. An elastic collision sounds a lot like inelastic collision. So just to preface there, we may be calling this non-elastic sometimes. So we consider a collision to be inelastic or non-elastic if the momentum of the system is conserved, but the kinetic energy of the system is not conserved. So we still have conservation of linear momentum, but we do not have conservation of total kinetic energy of the system. And again, most real-world collisions are going to be inelastic because some energy is always dissipated into heat. Thermal or sound. So in this example here where we have these two carts collide, I took the magnets out and now we're actually getting the bumpers of the carts colliding, and so it makes a pretty loud sound when they collide, and then there's a small amount of heat that is generated in the collision as well. And now a subset of inelastic collisions is a perfectly inelastic collision. So these are special types of collisions where if the two objects collide and stick together and move together after the collision, we call that perfectly inelastic. And not much really changes here. All the same rules for inelastic still apply. So kinetic energy is definitely not conserved in this collision. Momentum is definitely conserved in this collision. But we get to do kind of a math trick when we analyze these problems where, since they're stuck together, the two objects are basically moving as one object. So we can say that they have the same final velocity, and we can just call that Vf. So the two objects can be treated as one combined object. And so we see that the mass of the two-cart system afterwards, instead of calling it MA and MB separately, we can say MAB or MA plus MB in parentheses. And so the last type of example that we're going to look at here is something called a mechanical explosion. So a mechanical explosion is just when two objects are starting together and then something causes them to separate. So this could be maybe a compressed spring that's in between these two carts, held together by a locking device, and then pushing a button releases the spring. So that event of the spring decompressing is going to push the two carts apart. So that would be a mechanical explosion. It can also be as simple as if you're standing on a skateboard and you jump off the skateboard goes one way and you go the other way. That would be a mechanical explosion as well. So there's lots of different types of mechanical explosions. But going into this, what we see is that in this example, the carts are initially at rest. After the spring is decompressed, they travel in opposite directions. So the system could be initially at rest, or these two carts could be moving stuck together and then something causes it to separate. Now, one big thing about mechanical explosions is that the total momentum is conserved in this explosion. So once again, for all of these examples we see, we have total momentum being conserved, and that's a result of only internal forces acting on the system. We don't get total kinetic energy being conserved, and that's pretty clear in this spring example, because we have some stored spring potential energy, that's then being converted into kinetic energy of the two carts. So we actually see that the two-cart system has no kinetic energy to start, and then it gains some kinetic energy. And now remember, when we're talking about these collisions and explosions, we're talking about total kinetic energy, not just total energy. And that's one of the conditions that we're looking at here. So a pretty common question is, how can you experimentally determine if a collision is elastic or inelastic? Or alternatively, they might ask you to compare the kinetic energy of the system before and after a collision, which is in essence the same type of question. So a way to do this is going to be to check to see if the kinetic energy is conserved before and after collision. So if you take a look at the kinetic energy equation, the terms in kinetic energy are mass and velocity. So we're going to need to set up some experiment where we can determine the mass and velocity of each object before and after a collision. So say we had a collision between two carts, cart A and cart B. What we'd essentially want to do to determine if this is elastic or not is find the total kinetic energy of the two-cart system before the collision, which would just be Ka initial plus Kb initial, and then do the exact same thing for the two-cart system after the collision, so Ka final plus Kb final. Now, assuming the masses of each cart aren't changing here in this collision, all we really need to do to determine the mass in the system is to just take a balance or an electronic balance or scale and find the mass or measure the mass of each cart, and that will give us those terms which we can use to find the kinetic energy. The next thing we're going to want to do, because we have initial and final, is we need some experimental way to figure out the initial and final velocity of each object going into the collision and then coming out of the collision. So a good way to do this is to visualize the collision occurring on some track, and the way that we can find our velocity information is with a motion sensor. So this is a pretty direct way to measure the velocity of some object. Now, because we have two objects going into the collision, it doesn't really make sense to just have one motion sensor. What we really want are two motion sensors, each one tasked with measuring the velocity of each object during the collision. So we would set up our experiment something like this. We'd have motion sensor 1 on the left-hand side, motion sensor 2 on the right-hand side, and in between them, we'd have cart A and cart B on a collision course with each other. So motion sensor 1 is responsible for capturing the left object, or cart A's velocity, before and after the collision, and motion sensor 2 is responsible for capturing cart B's velocity before and after the collision. Now, sometimes we are limited by the tools that we have. We might not always have a motion sensor, but there is a way to do this with just more classic and more conventional equipment. So using something like a meter stick and a stopwatch, if we're assuming that these are going at a constant velocity beforehand, we could measure the displacement and the time of each object going into the collision, and the displacement and time of each object after the collision, and we can use that to calculate the initial and final velocity of each object. I think the best way to do this would probably be with the use of a slow motion camera, taking a video so that you get the time data and you get the distance or displacement data for each cart, and you can use video analysis, just looking at the video and where each cart is, to get that information instead of measuring it in real time. It's going to give you a much more accurate result here. So just to recap, what we've learned from these slides and from this video is that if there is no external net force on the system, then the total momentum is going to be conserved in all collisions and explosions. So breaking this down, for inelastic collisions, momentum is conserved, but kinetic energy isn't. Same thing goes for perfectly inelastic collisions. Momentum's conserved, kinetic energy isn't, but we get that added thing there where we have the shared final velocity Vf, since the carts move or the objects move together afterwards. In explosions, momentum is conserved. Again, kinetic energy is not. And then elastic collisions are that special type of collision where we get conservation of both momentum and conservation of total kinetic energy. And that's going to be it on this video going over elastic collisions, inelastic collisions, and explosions. Thanks for tuning in, and I look forward to seeing you next time.